This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
This March 21st and 22nd, don't miss Tech Ignite in Burlingame, California, just minutes from the San Francisco airport. Come to Tech Ignite to get rock-solid info and forecasts on adaptive cybersecurity, emerging technologies, machine learning and deep learning, operational intelligence, and much more. Join tech superstars Steve Wozniak and Grady Booch, plus C-level leaders from Netflix, Google, IBM, Salesforce, GE Digital, and Intel to gain valuable insights and learn about real-world solutions you can start applying today. Register now for the IEEE Computer Society's premier conference, Tech Ignite, at techignite.computer.org and discover the truth behind technology.
For Software Engineering Radio, this is Robert Blumen. Today I am here at the Dropbox corporate headquarters in San Francisco with James Cowling. James is the storage team lead at Dropbox, where he was the architect of the Magic Pocket distributed storage system. His other work includes consensus protocols, replication, scalable infrastructure, and cluster management. According to Wired Magazine, Cowling turned down a job opportunity at Google in order to work on this project. James, welcome to Software Engineering Radio.
Thanks so much, Robert. Glad to be here.
Is there anything else you'd like to tell the listeners about your background?
That's a pretty charitable bio that you've given the listeners, so thank you for that. I guess you can tell that I'm Australian, so I'm from Australia. I've been at Dropbox for about 5 years now, and came here out of academia. I used to be in research, and I came here into industry, and it's been a great time ever since. So, yeah.
Great. Today, I'd like to talk to you about Dropbox's migration off the cloud and the Magic Pocket system that you built to replace cloud services. Wired Magazine did a piece on this called The Epic Story of Dropbox's Exodus from the Amazon Cloud Empire. We'll link to that in the show notes, and I'd like to explore some themes from that article and from your engineering blog. To start with, describe Dropbox.
Yeah. So hopefully most listeners know what Dropbox is by now. It's almost a noun. And Dropbox originated as the magic folder. So Dropbox is a folder on your computer that you put files in, and they're synced to all your devices. They're synced to the cloud. Since then, Dropbox is working on a lot of features around collaboration and kind of getting work done. But at the core of the business, there's a lot of storage that goes on. And what I work on at Dropbox is this storage part of the equation.
Can you give us any data about how big Dropbox is, how many users, how much data?
Yeah, certainly. I can give you kind of the latest public figures that we release. I think we've said we have over 500 million users, so it's a pretty big number. I think over 200,000 businesses that use Dropbox for their work. In terms of actual data scale itself, the last number we released a long time ago now was 1 billion files synced per day, and that's obviously grown over time. And in terms of the magnitude of the storage itself, we have multiple exabytes of data in our storage systems, which would put us in one of the biggest kind of storage providers in the world.
What unique requirements does Dropbox create on your infrastructure?
Every large-scale infrastructure company has different requirements, right? And so if you look at companies like Google, it's a very compute-heavy company. Companies like Facebook, latency matters a lot to them. They're quite compute heavy. Some of that data is quite ephemeral. It's news posts that you might see for a brief period of time. For Dropbox, people entrust the most important files to us. So we are very storage heavy. We have a lot of storage at Dropbox. Also, we have very high requirements on durability and availability. And you can imagine if you're putting your business documents or your passport scans or or that kind of information that you absolutely can't lose, and you need it whenever there's an incident, for example. That means that for Dropbox, is really intense focus on durability, correctness, and availability. And these were kind of the design constraints that went into building the storage system itself.
Tell us about the history of Dropbox prior to building your own infrastructure.
Yeah, so Dropbox has been around for, I guess, close to 10 years now. And fortunately, from the very beginning, Dropbox was what we'd call a hybrid architecture. And it was a very wise move. Maybe it was an accidentally wise move back then. It was very early on. But the very first version of Dropbox ran on Drew Houston's, our CEO. It ran on his computer, his laptop. Right? And then pretty soon afterwards, it was running on a single server, and we had too much storage to run on a single computer. And we used S3 for the storage. So very early on, even from the very beginning, the storage was on Amazon S3. But all the business logic was on our own servers. And as the company grew naturally into a real business with hundreds of millions of users, the scale of that metadata and the business logic increased over time to the point where we have multiple data centers running thousands of database machines, multiple petabytes of metadata, and all the compute that goes along with that, but still leveraging the storage of Amazon S3 and various other services. Like Amazon has a huge suite of products, and we're very open about leveraging third parties where it makes sense. So stuff like SES and SQS and a whole bunch of acronyms that start and end in S that we've used to leverage to build our business out.
Briefly describe what is S3.
S3 is Amazon's simple storage service, and it's a storage as a service platform. It provides an API to put files and retrieve files. And many companies on the internet use Amazon to handle their storage. And it's a very wise move. Any company should focus on their core competencies, right? Leveraging the skills that they're uniquely good at. For most companies, they're not uniquely good at storage. Storage requires a lot of specialized skill sets, a lot of teams that a lot of companies don't have, capacity management teams and hardware teams, etc. And leveraging a third party like Amazon makes a lot of sense for them. It made a lot of sense for Dropbox for a considerable period of time. It only got to the point where we were really one of the biggest players in the storage game that it makes sense for us to invest in building our own storage platform and tailoring it better to our use cases for better user experience, better performance, lower latency, better resource utilization, etc. Because we're at the scale where we could do things better for our own use cases.
So you wanted to do things better for your own use cases according to all those criteria that you just named. Now, in what respect was it not possible or maybe not cost effective to do that on S3?
S3 really did give us pretty good performance. And so one of the kind of unintended consequences that came out of this story is that it was, in some respects, pitched as a story of Dropbox's exodus from the cloud. Dropbox is a cloud provider ourselves, right? And we're quite enthusiastic about cloud services. We use Amazon still for a lot of our business. But it got to the certain point where we could do a bit better. For example, S3 has a hard job. Right? They have to provide a storage service that works for every startup out there in the world. Right? Most of those companies are much smaller than Dropbox. They have much smaller data volumes, and they have their own unique workloads. For Dropbox, I know very intimately what our workload looks like. I know that if you upload a file to Dropbox, that there's a spike in reads in the first hour, that drops off at a certain point, that tapers off over a certain kind of gradient over time. We know how big those blocks normally are that comprise these files. And that information allows us to build a storage system that's tailored very closely to our workloads. So, storage systems where you can, over time, use the kind of the minimal level of CPU overhead and RAM and network to provide the kind of guarantees you want to your customers. That's advantageous from a cost perspective, but particularly it's also advantageous from a technical perspective. We have 3 to 5 times lower latency across our percentiles than we did on S3. That said, we're pretty happy with our latency already on the back end. It also provides a platform that we can use to build new features. Right? We can place data close to our users now because we have control exactly where we put that data in the country. We can use all the tooling that came out of that project, the tooling, the monitoring, the capacity management, etc., to build new products inside Dropbox, new infrastructure products. So it was a big kind of leveling up of the infrastructure team here. But it really came from a situation where we felt like we could have a competitive advantage and we could do better, and not that we were that dissatisfied with the status quo already.
I'm going to say something I believe condenses several points you made here, and you tell me if this is what you actually said. The typical application doesn't create any specialized needs on infrastructure. The typical cloud provider is going to provide a range of general purpose machines that work most of the time. If you're small and it doesn't quite fit what you do, it's okay because you make do with what you have. But there's a point where you become so large that the gap between what you're getting and what you could build yourself, if you really optimized it, justifies taking on this huge cost to make something that's just right for you.
Yeah, I mean, the Magic Pocket story sparked a lot of conversations on hack and use in these various places, and there were great conversations, but a lot of the comments of people saying stuff like, you're an idiot if you use a cloud provider because they're so expensive. And that's just not true, right? You know, if you want to build a storage service as reliable as Amazon S3, it requires a lot of investment, right? And for Dropbox, for example, you know, we store all user data in multiple geographic regions. We can lose the entire East Coast and keep running and have no data loss and no availability issues. That level of durability and availability is a significant step beyond what you'd get from a small on-premise storage operation. And the likes of Amazon S3 of the world are kind of providing that level of service to a large degree.
I understand your rationale. At the time, was this decision very clear within Dropbox, or was it controversial?
Well, at the time, if you think of when the project originated, it wasn't clear. You know, it was an aspiration. I mean, you know, wouldn't it be great if we could build a storage system? But it was totally unclear at the time whether we were capable of doing it, or at least capable of doing so in the short term, and what it would entail. And so, our job as engineers was to take controversy off the table. Right? There was no point where we were going to launch a storage system that was controversial. Right? It was no point where we were going to go and say, "Hey guys, we're deleting all our data from S3. We hope it's safe." Right? And so our job was really to kind of build a very smooth transition and trajectory where we ramp the system up very slowly. You know, starting from 2 engineers, building a prototype and experimenting and scaling it up. It's a very low resource consumption, just 2 engineers, right? To, you know, eventually a big team and big hardware purchases. But these were all leveraged on previous experimental decisions and increasing our confidence as we went. So by the time, you know, what you hear about in that wide story was when we were ramping up very fast. We were bringing on 30 to 40 racks of storage a day. And these are very dense storage towers. These are racks with multiple petabytes in them. So it's a very steep ramp in storage, but this is only once we'd gone through a very long proving period. And during that proving period, we stored some of our users both on Magic Pocket and on S3 while we gained that confidence. We had this like extensive production validation period where we made sure we were absolutely confident from an operational perspective that we could keep this storage system running and we could provide the kind of guarantees that we wanted. So by the time we launched it, it was totally uncontroversial. But I think it would have been very controversial if we decided on day one to build the entire storage system, flip everything over in one day. Yeah.
You mentioned a moment ago that most organizations don't have a lot of expertise in infrastructure, or especially in storage, which is a specialized niche of infrastructure. Did you have the skills you needed within the company, or were you having to hire to bring in specialists who knew about building this type of system?
Yeah, one of the interesting things that came out of this project was just the breadth of roles I think you don't even realize you need early on. And when we started, we had a lot of smart, driven engineers who had a good grasp of distributed systems and architecture, etc. But we didn't have an extensive hardware team. We didn't have hard drive experts. We didn't have a large networking team with experience in backbone networks and metro networks and transit and peering and all that kind of stuff. We didn't have a capacity management team. And that's one of the interesting things. You know, you can imagine running out of space on your hard drive on your laptop is a pretty big deal. You obviously can't run out of space on a multi-exabyte storage system. And so there's a lot of supply chain management that goes into that. I remember a time when we were ramping up the system very quickly. We were adding maybe 5+ petabytes a day. And we had 2 trucks crash in 1 week. So we had 2 big kind of tractor trailers delivering racks. They both crashed in 1 week. The drivers were fine, but we lost a lot of storage hardware. That could have crippled a company that didn't have a very mature supply chain organization that already baked these assumptions in, being able to deal with vendor shortages, etc. So there's all these roles that you don't expect, I think, ahead of time. But fortunately, we were able to hire a lot of great people to help build this. And that team really went from, originally was a small group of engineers to being a really quite large multidisciplinary team over time.
You mentioned the network engineering component. My experience with Amazon is that you can get a server from them and it'll be the server you want. It has a certain amount of memory, storage. They'll make some guarantees about the performance of the storage, and you have a lot of control over the server, but the network is more opaque and it's less clear what it is they're promising you. How much was gaining control over the network important in order to deliver the end product you wanted?
Well, it was important in various ways. One way it was important is because we have multiple services at Dropbox. We have storage, but we have all sorts of processing that goes on that storage. For example, if you upload a Word document to Dropbox, we generate a PDF preview of that Word document for you, so that if you try to view it on your phone and you don't have Word installed, we can show you a render of that document and you can read it. There's all sorts of things that go on behind the scenes to make Dropbox like a very seamless user experience. If you upload a video, we H.264 encode the first 5 seconds of that video, so we can start streaming it to you on your phone or on your laptop. So we have a lot of services that read data in Dropbox and process it, etc. So being able to co-locate them with the storage was advantageous. Being able to have management of our peering relationships was advantageous. You can imagine the volume of data we push at Dropbox is huge. It's in the terabits of network capacity. So there was a lot of investment in kind of the efficiencies within our network stack. On the topic of networks, another interesting part was just getting that data into the storage system to begin with. And so there was a 6-month period where we brought over 500 petabytes into the storage system, out of Amazon and into the storage system. And so that, you can do the math, and there's hundreds of gigabits nonstop of traffic moving into the storage system. And that was only possible with kind of very close relationships with Amazon and peering relationships, etc., to pull that kind of volume of traffic into the system.
I'd like to shift now and talk about the Magic Pocket system. Before I ask you about the system, I have more of a meta question. What were some of the principles and philosophies that guided your design thinking?
Everyone who's involved in the project is familiar with other storage systems that have been built. There's only a certain number of ways to build a storage system. And we're familiar with distributed systems literature. And so we all have a good architectural sense for how to design these systems. There's a big gulf from designing a system in theory to actually pulling it off in practice. And one thing that we're kind of well aware of is that you have to build really simple systems because the complexity comes over time. When you have literally hundreds of thousands of nodes in a system, it just gets complex, no matter how simple you design it. So I guess the most important principle, well, there's 2 really important principles. One of the most important principles was keep it simple. Like every design component had to be really simple, not over-optimized, not over-thought. One example of that is early on, we have a storage index in our storage. So we have multiple tiers of storage indices, but one of those maps a block to its logical place within the system. It's in a huge database. And originally, we had planned to build our own in-memory key value store, a huge one, for performance reasons. But we decided, let's just use a big MySQL database. Let's use a big sharded MySQL cluster. It's too much to think about right now to design our own key value store at the same time. We have a lot of expertise at running MySQL databases. Let's just use a big sharded MySQL database for this part of the system. We planned on replacing that, but it turned out it worked great. And we still use this giant database. It works perfectly. And that just saved the complexity of a custom in-house key value store that we didn't need. Right? The other principle I was going to get to is what we call in the team 100% correctness, or getting to 0. Right? And that means we need to ask ourselves at any point in time, is this system correct? Like, is every piece of data in the system valid, correct, uncorrupt? Right? And we want to be able to say no with absolute certainty. and have constant verification systems that kind of verify this. And if there's ever a spike in that graph, if that ever changes, we know something went wrong, right? And so having that verification coverage and knowing that everything's correct today gives us like a lot of insight into correctness moving forward. And this sounds like an obvious thing, but if you kind of ask around people who've been in the industry for a while, most databases and storage systems have a lot of inconsistencies in them. You know, oh, that data looks weird because 5 years ago Bob did something, blah. And it's very easy for that noise to inhibit your visibility into the behavior of the system. So for us, absolute zero compromise on errors in production. There's always errors in testing. We're human beings, you know. But you have this big release process with very stringent kind of verification coverage to make sure that every bit in those disks is correct. You know, every bit in the index maps correctly to the disks themselves. And in terms of building the system, that meant more code. I haven't seen the line counts recently, but I would guess that a similar amount of code goes into verification coverage. Probably more code goes into verifiers than the storage system itself.
This makes a point that invariants help you reason about a system. Do you agree with that?
Absolutely, and they help you move faster as well. You know, I think if you're prototyping a startup and you just got to move fast and get stuff done, that's fine. Maybe the invariants will slow you down for a couple of days. If you're building a large system that has to be durable with, 12 plus 9s of durability, the invariants and the test coverage make you move faster. You know, it's much easier to push code because you know you're going to be able to detect very quickly if there's an issue. And that's something we invested in early on, and it really paid huge dividends. And there's actually the technical blog where we go into the verification stack on the Dropbox tech blog that people can check out. A lot of examples of the kind of verifiers we used, so we didn't even have to trust our disks were storing the right data, for example.
I'll make sure we link to that blog post in the show notes.
Searching for a new job is stressful and scary. Then you go through the interview process only to find the salary offer or company culture doesn't match what you're looking for. Hired.com is the world's most intelligent talent matching platform for engineering. We make your job search faster and stress-free. After completing the application, top employers apply to hire you. You receive personalized interview requests and upfront salary information. Your dedicated advocate will assist you, providing career coaching to help you with potential employers. Hired.com hides your profile from current and past employers to respect your privacy. The best part? It's always free. Today's SE Radio listeners can earn a $2,000 hiring bonus by signing up at hired.com/SERadio. Find your next chapter at hired.com/SERadio.
So what are the main use cases of the system?
The main use case of Magic Pocket is storing users' files. The vast majority of what's stored in Magic Pocket is files users uploaded and serving them to users when they request to view them.
You have writes and reads.
Writes and reads. It's an unusual workload because most people think of storage systems as having a very high read to write ratio. You know, you write something once, but you read it a lot. With Dropbox, we have an unusual scenario where we have one of the world's largest caches, which is people's computers at home. Right? People have their Dropbox account, but their files are typically on their local laptop as well. So a lot of the reads are served locally off their computers. So within the storage system itself, we have a much closer to 50-50 ratio of reads to writes. So it's a very write-heavy system.
Let's talk about the architecture. Give an overview of the architecture of the Magic Pocket system.
It's a big system, and so it's hard to describe in detail. People can go to the tech blog to see the architecture, but I'll give you some fundamental principles. So the first is there's concepts called a zone, and a zone is a geographic region, and they're completely autonomous, opaque geographic regions, and we make sure that all data is in at least two zones. The two zones run different versions of code. Their operational scripts aren't allowed to run across two zones simultaneously, and that's our hedge against large-scale disasters. You know, a meteor hitting a city, or someone operated running a really bad script that manages to kind of destroy a zone. Then within a zone, we have an architecture where you have an index that maps a block's a portion of a file, to multiple locations on disk. And there's a lot more components in it, but essentially it's as simple as that. An index, this block is replicated this many times on disk. Now, for live writes, they come into the system and we pick a number of random disks to write to spread that data around across multiple racks and rows and facilities for physical redundancy. And then in the background, we erasure code that data. So we apply something similar to an algorithm called Reed-Solomon to give us the same level of redundancy, of storage redundancy, but with a lower level of storage overhead. And for us, that's one of the games you've got to play is you can't compromise on durability. You have to be able to handle a large number of correlated hard drive failures, but you want to do that with the minimum number of hard drives. No one wants to be wasting storage.
Let me see if I understand this. A file comes in. The file, if it's big enough, it'll be split into blocks. This index, which is the MySQL sharded index, tracks the mapping of Robert's file to a bunch of different blocks, which are on different hard drives throughout the zone. And then you copy it over to another zone just to make sure you've got 2 copies of it.
So you have full redundancy within a zone. Each zone has very high durability. We've never lost data within a zone. But we had those 2 zones there just for the disaster scenario. And then you have internal processes that deal automatically with failures, because in a system like this, failure is just a norm. Failure is not an unusual event. When you have hundreds of thousands of disks, they fail every day. That's just the disk life cycle. And so the system's designed to automatically re-replicate whenever there's a failure. So if you lose a disk, there's systems that detect that, make sure that data is very quickly re-replicated elsewhere in the system. And to a large extent, it's a hands-off operation. We've developed the operational maturity right now that the system manages itself to a very large extent. We go through a disk remediation lifecycle we talk about, where I'll give you an example of this. So you can't have operators manually detecting disk failures. And you don't want operators on scooters. Some companies do this, but we certainly don't want people on scooters riding around the data center, pulling disks in a hurry and putting replacements in, because that's open to operator error, right? You don't want operators having to do anything on a live system. So if you lose a disk, we let it fail. The disk is dead, and we have some systems that automatically try to recover it. Maybe if it's a bad sector, you repair that sector, bring it up again. If it's a bad file system, maybe you repair that file system, bring it up again. After a number of attempts, the system detects this disk is bad, something wrong with this disk. It waits for that data to be fully re-replicated, so we know that there's no dependency on that disk. We don't want to take that disk to a lab and try to get stuff off it. It's fully re-replicated elsewhere. At that point, we mark that disk as gone, and the system keeps running. And only very infrequently, that system also files a ticket for the data center operations folks, that eventually they can come around asynchronously and replace disks at their leisure in bulk and destroy them on site. But there's no live manual intervention required. And that's very important for durability. If we lose a disk on a long weekend, we don't want to be vulnerable to data loss because we're waiting for an operator to come around and swap it out. Everything's automatically re-replicated very quickly.
I understand from Wire Magazine you designed your own servers. Tell us about why could you not use existing servers? Why did you have to build your own?
Yeah. So this is something else that comes in that kind of timeline of expertise. At first, you've got your hands full just designing a system, building the operational tooling to get it working. But at a certain point, that's starting to get stable, and you can start focusing on the hardware profile. So up until this point, you view hardware as a black box.
Yes, this is software engineering radio. We think hardware is a black box.
Hardware is you probably think you write something to a disk and the disk actually stores it. But many times it doesn't do that, right? It says it does, but it doesn't.
Yes.
So at a certain point, you have to stop seeing that hardware as a black box and actually look through the stack. And we got to the point where we wanted to increase our storage density, primarily for cost reasons, and take advantage of the latest generations of hardware. So we had a project called Discotech, and Discotech was the disk technology team. And their job really was to look across the stack. So our first version of the system just treated hardware as a black box, and we had a file system on that disk, and the blobs, the blocks of data were packed into extents that were stored in that file system. And the new system completely rewrote the stack. There's no file system. We directly schedule the disk ourselves. We issue ZBC instruction codes to the disks to schedule them. We have our own SSDs on the disk to do caching, etc. And that process allowed us to take advantage of new technologies like SMR. SMR is a technology, it stands for shingled magnetic recording. It's a new type of disk drive that gives you 30+% more density, storage density for lower cost. But it's primarily an append-only storage mechanism. The dynamics of how the disk is laid out mean when you write a track, there's leakage into the adjacent track, and it performs quite poorly for random writes. So we rewrote our storage system to be append-only, strictly, and we had this very close alliance between the hardware team and the software team to design a storage chassis that meets our needs. And we have a couple of these. You want to have a lot of diversity in the hardware profiles that you use. But we have this kind of platform which we call a discotheque box, which is a 4U rack mount server that stores a little bit over 100 drives. And they have varying disk densities. As new disks come out, we adopt them. But you can think of these as storing over a petabyte of data in a single 4U rack mount chassis.
And what is 4U?
Oh, so yes, sorry. So a U is a unit. It's a standard measure of rack height. So a typical rack might be 40U high, 40 to 44U high, depending how tall your server rack is. So you can store, depending on how big your rack is, between 8 and 11 4U servers in a single rack. And so you're talking, around 10 petabytes potentially, 10 petabytes or more in a single rack in a data center.
Something I'm curious about, programmers are trained to think in layers. We have to have layers because it's a way to manage complexity.
Yeah.
And you think about the layer underneath you, it is a black box. You have to trust that it's going to do what you think it's going to do, and you focus on writing your layer. Like you're saying, software engineers, we think storage is a black box. To what extent did your software engineers need to really understand the characteristics of the hardware in order to implement something that would in the end meet your requirements?
Yeah, layer violations are always ugly, right? We're huge believers in strong APIs and very simple, clean APIs. And to a large extent, you can avoid layer violations by understanding that the layer below might fail to meet its obligations. So you might tell a disk to f-sync, but it gets lost because of a sector error or what have you. And so you have verification systems that span layers. So for us, most of the verifiers are kind of cross-layer verifiers to verify what we think is correct on one layer is correct on the layer above. But there were times where we had to work across layers. For example, there's hundreds of kind of facts that go into the design of the storage system. One is in these SMR drives, they typically have these independent write zones that are typically 256 megabytes wide. And so we wanted to make our extents that we put on these disks multiples of 256 megabytes. There's a lot of facts like that and nuances that went into the kind of the architecture and the constants that go into the storage system. It's unfortunate to engage in layer violations, and I think people should avoid it as best they can. But at a certain point when you really want to eke out efficiency, I think it's necessary. But this is what I said earlier in the podcast, the complexity comes, right? You have to have a really, really simple system because eventually you start saying, hey, maybe we should start using SMR drives rather than the current PMR technology. If you have a complex storage system, there's absolutely no way you can retrofit that in. The complexity comes as you go. So I think focusing on very, very simple APIs, very, very clean layers, allows an occasional layer violation for performance reasons.
I want to change the subject and talk about Rust. You had a lot of code written in Go, but you switched to Rust, which we did a show recently on Rust. What aspects of the Go language were not meeting your needs for this project?
Yeah. So we've actually gone through 3 languages on this project. So the original prototype was in Python, just because we can move fast and we were just playing around with architectures. But once it became clear we wanted to have a really durable, large-scale system, we rewrote it in Go. The strong type system helped a lot there, the concurrency support, the memory efficiency. To a large extent, we are very happy with Go, and Go is still the primary infrastructure language at Dropbox. The way we think about language here is that having a minimal set of languages is advantageous. Right? You want to have common libraries and minimize language proliferation, but you want to use the right tool for the job. Right? And there were use cases where we wanted a more C++-like language without having to use C++. One good example was the OSD, which is the code name for the storage device. And this is a device where there's hundreds of thousands of these, and the minimal amount of RAM and CPU we use, the better. And so we wanted to have very explicit memory management on these devices. So we wanted a non-garbage collected language that we could do a lot of manual memory handling. A lot of developers here love the type system that comes with Rust. They love the expressivity of the type system, and they wish Go had generics. But personally, I'm a huge Go fan myself, and I primarily write my code in Go. But I think there are some use cases, very large scale, or where resource consumption is very important, where Rust makes a lot of sense. People here love the language. They love to use it.
Was memory management the main driver of choice of Rust in those cases?
Yeah, I think initially memory management was the main driver. I can't remember what version of Go was at when we started doing this. Probably Go 1.3. And the garbage collector's improved a lot since then. But we were suffering pretty significantly due to GC pauses and kind of buffer bloat. That's much less of a problem these days. But still, this is you can imagine the storage nodes are boxes that push terabytes very frequently through the system. They're handling very large buffers, so we could get better memory management doing it ourselves. But like I said, personally, I use Go primarily, myself.
This issue of GC pauses, it's come up in several of our shows. We did a show on latency, which was mainly looking at latency that users perceive. The user is waiting for some operation which somewhere is getting queued up behind a garbage collection pause, and that translates into end-user latency. Was it end-user latency that you were concerned about, or how did garbage collection pauses at that deep of a layer turn into a problem?
It's a astute question, because the reality is very infrequently did they make it out to the user, because there's just so many layers on top of this system. And the volumes of data you're pushing around are so large that typically a GC pause is not affecting. It's not like a database where you're doing very high QPS. Primarily, it was our internal operations. Stuff like repair traffic and pushing around large buffers that were issues. Also, just the keeping the size of the free memory pool under control was also an issue for us on the OSDs. We do see GC pause issues in Dropbox, and there's a pretty crude solution to a lot of these things, which is to run more processes per box. Magic Pocket has a storage nodes, but it has a lot of serving traffic as well. And, we run 16 processes per box sometimes just to keep the heap size smaller for the sake of memory management and minimizing GC pauses. I've heard the new version of Go has a better garbage collector again. It's getting better every day. Maybe we don't need to do that anymore, but that's something we'll experiment with soon.
I'd like to talk now about the move. How did you cut over from S3 to Magic Pocket?
Yeah, very gradually and very carefully. And so for the longest time, we had some small fraction of users, say 10%. It got to 30% eventually, that were stored simultaneously in both Magic Pocket and in S3. I remember the date very viscerally because it was a big kind of point of celebration when we began the period called production validation. And so at this point, we had a fairly large storage system that could store around about 30% of our data. It was running in multiple geographic regions. And we said, okay, from this day onwards, we're going to treat this as our primary storage system. But we had the data in S3 just in case. And there was an absolute zero tolerance policy for errors. If Magic Pocket went down for any reason, we had to kind of reset this launch clock that we had. And we wanted to run for some considerable period of time, many months, of uninterrupted, seamless operation. There was one point in time when we did have to reset the clock. And I can go into more details on that. But once we finished that production validation, we were very confident in the ability of the system to scale and operate durably. And then it was a period of it was quite difficult, of logistics. Buying as much hardware as we could and bringing it up as quick as we could and funneling data into the storage system as fast as we could.
Since you said you could go into more detail about that, there must be a good story there.
Yeah, so one of the things you want to do in a system like this is protect yourself from yourself. Right? And we all had, we live and breathe durability and correctness here. We have a vested interest in seeing the system launch as well. As engineers, we're so excited about the system, we want to launch it, right? So we didn't want to have any slippery slope arguments. So we decided before we went into production validation, we wrote a little contract for ourselves and we shared it with the Dropbox founders. And it was, here's the conditions for production validation and here's the reasons we'll reset that clock. Any major outages, any major bugs that make it to production, any data corruption, anything like this. And so we had this big long list. And there was a point in time probably a month and a half into production validation, where a bug made it to our staging cluster. So we have, testing cluster, then eventually the data goes to a staging cluster, which stores a copy of data, and then it goes to our production clusters. And a bug got that far, and it didn't actually cause any data loss. There was no data loss, but we kind of got lucky. We didn't see it coming. We didn't catch that bug. Our verifiers didn't detect it, and it happened. And we hadn't violated the rules of the production validation, but we all felt a little bit dirty about getting a free pass. And so we went to Akil, who's the VP of engineering, and said, "Hey, Akil, we want to reset the clock." And he said, "Great, proud of you guys," kind of thing. And we reset it and we started again. That cost money. That pushed the launch of the system back quite a lot. But I think we wanted to launch the system in a place where we were really, unconditionally confident in it and not confident by technicality.
I'd like to wrap up here with some questions about lessons learned and what we can take away from this. In retrospect, what were some of the major lessons that you learned from this migration?
A lot of them. One of my favorite examples is just, when I was doing my PhD in distributed systems, I just didn't have a grasp of the real world in terms of it being people and bits and hardware, right? And that some of the problems you're going to face is stuff like the cooling system breaking or a truck crashing, or we had a problem where we just couldn't fit any more racks in the loading dock. We couldn't put any more hardware in because the loading dock was full. So there's a lot of, when you get into the real world, the practical realities make it much more exciting but much more difficult. That's one of the lessons learned. I think in hindsight, if you think what we would have done differently, the product went well. But I do wish we'd invested earlier on in operational automation. So for the longest time, it was fairly stressful to be an engineer in the project because there's a lot of things, a lot of hardware breaking, a lot of manual intervention, if you had that many boxes, they break in all sorts of weird and wonderful ways, and we had to manually fix them. And that was very distracting, and it kept slowing down our progress. And eventually we hired some folks who had a lot of experience in kind of a lot of automation around this, and built a very strong SRE team, a site reliability engineering team, who took over building tooling to automate all these processes. And that got us to a point where we had much better correctness because there was no operators getting manually involved, but also we could focus on actually building things, right? And so I wish earlier on we'd done that, but it worked out fine in the end. And I think the last is this something you mentioned earlier on, which is that the importance of simplicity. Systems get really complicated. Never do something because it looks cool or it seems fun, right? I think within the team, the culture is, if you could get away with not building a system, then don't build it, right? Because what matters first and foremost is achieving the goals, which is having a durable storage system. If there was an off-the-shelf product that worked great, you better believe we would have used it. But there wasn't, right? And so I think keeping it as simple as possible because, as I said, the complexity comes with time.
Most of us are not ever going to be involved in migrating exabytes of data from one storage system to another. But it's very common that you need to move off of an old system onto a new system. Happens all the time. What are some advice you would give to people who are in that kind of process that they could learn from your experience?
Yeah, I think the number one is always have an undo button. Right? You want to never get rid of the original source until you're just incredibly confident in the new one. And no matter how well you design it, architecturally, there's going to be operational issues that slow you down. So I think doing that changeover in a way that can be seamless is really important. For us, that meant having a system where we could seamlessly migrate users across without them knowing. And the other one is that every engineer wants to redesign something, right? It's a very natural impulse for an engineer to want to build something from scratch because everyone likes building new systems instead of maintaining systems. I think people should think very carefully before they do that, right? They should have a very good reason for why to rebuild it because the design is going to be a lot better. It's going to be much more efficient for these reasons. And a lot of migrations, I think, come out of situations where it wasn't necessary, right? But I think in a system like this, where it was made a lot of sense for us to build a system on our own, the big key was doing it slowly and having a lot of opportunities to turn back if anything went wrong.
I think that's a great place to stop. James Cowling, thank you so much for speaking to Software Engineering Radio.
Great, it's nice to be here. Thanks so much.
You can reach us with feedback by email, team@se-radio.net, on Twitter @scradio, our Facebook and our LinkedIn groups. For Software Engineering Radio, this has been Robert Blumen.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter @SE Radio, or search for the Software Engineering Radio group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.